Hello, everyone. Hello. We're very happy to have Inbar, who will speak about learning dynamics of non-convex models in high dimensions. Thank you.
Thank you very much. What I'm going to talk about is the high-dimensional limit of an algorithm, a stochastic algorithm. What we show is that this algorithm converges to a set of ordinary differential equations, which we can analyze, and then provide a lot of information about performance and understanding of how the algorithm actually works. Okay, so let me start with what is actually optimization in high dimension and what am I talking about. So in general, in the context of machine learning, what you will have, you will get a set of samples that are drawn from some unknown distribution. And typically what you would like to do is some kind of minimization over some function. And now it's a random minimization because I'm summing over all my samples. And so this is in general what people want to do in the context of machine learning and minimizing over a set of parameters. But actually, what you would have wanted to do if you would have had some access to this unknown distribution P, you would have liked to actually do the minimization with respect to this true distribution. So then it kind of, the problem is that there is no such, a priori, you don't know that this indeed will be the right minimization.
Where do I see P in this thing?
Oh, so the P is the distribution of A and Y.
But in this formula, why do I see?
Oh, it hidden inside the expectation. Okay. So if I didn't write the expectation.
Now you have an expectation, which
yeah.
you wouldn't have.
Yeah. So the idea is that, and the reason why I write it in terms of A and Y is in most problem, what you will get an input, which can be, for example, an image. And you want to, let's say, classify, say, okay, that image should be a dog, a cat, or whatever. So that would be the label of that image, Y. And what you will get is a sequence of this image with their labels. And based on this sequence, you want to kind of know how to, if you will get a new image, what to do with that. What will be that label? And what I will discuss in this talk is what happens when you want to do this minimization, when the number of samples that you have is large, but also the number of parameters, the minimization that you're doing over this X can be very, very large. And this is kind of motivated also by practical use of this, when you talk about machine learning algorithm. And if you think about the number of parameters that you have today for algorithms, it's around the billions and sometimes even trillions. This is really what is actually being done today.
Right, that's for the N, the D.
That's the D. But actually, that's a good question because the N is also very large. They are proportional. Usually, you can actually assume that they are proportional to one another. That's a reasonable assumption to make, and this is the regime that I will be talking about today. So let's discuss a little bit about how do we actually do this minimization. So I will discuss about one possible optimization algorithm. There are many. There is many others that one can consider. So what I will talk about is something that is called online stochastic gradient descent. So first of all, if you want to do this minimization, what will be the simple thing that you will do? You will do gradient descent, right? Steepest descent. The issue in this context of high dimension is that when you want to calculate this gradient with respect to billions of parameters, this is very heavy. And now you want to also average over many examples. So that will be, it will take you a lot of time to just do one step. of iteration of gradient descent. So what people typically do, they don't calculate the gradient for all their samples at a time, at each iteration. They just take a few of them and calculate according to that. And let's take that to the extreme. What we will do today is that at each iteration, we will take just one sample. And in general, what the idea is that you want that if you do enough iterations, you will converge to the true estimation of the gradient. And to simplify the situation, what I will assume today is that you have a stream of data and you cannot reuse samples. I will talk about in the end what happens if you reuse sample. This will be an extension, but for now, let's assume that this is the case. And again, I will be working in this limit that samples, which is number of iteration in my situation, will be proportional to the number of parameters that I'm having. So for now, this can be thought of as just a Markov chain that I'm just at each iteration, I'm taking new samples of my data. So then it's like random addition at each iteration. Okay, so as we do this stochastic gradient descent is a well-known algorithm in the context of optimization and machine learning. And so what new can we say about it? So let's start with what happened in fixed dimension when D is actually small. You're just doing this iteration with just a few number of parameters. So when you do that, so that's already go back to the 50s. So what people have shown is that in this, and when the number of parameters is not infinite, then if you take the step size to be very small, and you take the number of iteration, which is number of samples, to be very large, you will have law of large number, and you will converge in the end to something that is called gradient flow, which is an ODE, which is now with respect to the population error. So if you would have actually have this unknown distribution P, and you would average according to that. So that actually will give you this gradient flow, which is great because this is actually what we wanted. We wanted in the end to do the average with respect to the unknown distribution P. But what happened in infinite dimension? So in infinite dimension, the problem is that you cannot really take the step size to 0. Because the number of parameters is huge and it's proportional to the number of samples, if you will actually want to do that, then it will take you infinite training time to train in order to arrive to this limit. So one of the questions that we will ask today is how can we understand this high dimensional limit, and is there like some kind of equivalent between that we can study in this field? So just to put you like in there an example, because this is up to now is very general. So in the context of machine learning, so suppose that I had this AI and yi, which are drawn from the distribution P, and I have n samples that sort. And now you can think of AI, for example, it can be each sample that I'm getting can be an image of a cat and a dog, and 0 and 1 can be a classification, whether that's a dog or a cat. And I can take these pictures in many different poses of that dog and cat. So what is my task now? I want to find what is the probability that this image now is a cat or is a dog? So how usually people do that? So they want to find this mapping between AI and yi, the connection between the two. So how do we do that? So you try to build a function that will characterize this probability. So let me give you a function. So what will be the function that I'm thinking about in order to represent this probability, and then what I will do is I will try to find the best parameters x such that I will have a good mapping between AI and yi. So this function is something like that has this following stored. So that's like going between 0 and 1. And what I want is actually that when yi is equal to 1, then I want the g that will be closer as possible to 1. So it's kind of a smooth threshold. So in the end, I'm building some kind of a distance between yi and my function. And what I want is that my function will be as close as possible to y. So the minimization process that I'm doing now, if I'm going back to my function, is just to take the minimization with respect to this distance. When I'm summing over all my samples. So now how do I do this minimization? I will do just stochastic gradient descent. And what I'm going to show you today is that using our theory and our equation, we can provide an exact equation to what stochastic gradient descent will do without even running it. So, and as the dimension of my problem is growing large and large, our formula will be more and more exact. Okay. So this example can be represented in a much general set of examples, which I will need in order to, because we cannot really specify this theorem for any distribution field. So we do make some assumptions. And this idea is something that is called in the context of machine learning to think about is some kind of teacher-student model. So what is this teacher-student model? So we have some assumption of how the data will generate. So this is you can think about it as a kind of as if you are the teacher and you generate the data for the student. Okay, and you give the student a few n samples of your data.
When I look at a picture and say it's a dog or a cat.
Yeah, and you build a function that kind of as I did for the logistic regression, you build a function that says, okay, that will be a dog now, and that will be a cat. That's what as a teacher that's what you're doing, and you can also add some noise to each image that you're taking. And in particular, what I will be focused on, the type of models that I will be focused on. So you have some unknown parameters that you chose, and you don't tell that to the student. And in particular, what the type of function that I will be interested by is if you have inner product between the image that you have or whatever vector that you take as your input and the parameters, such that it's a lower dimension. So in the end, you're taking a function that will be a lower dimension of the true image that you're taking. And so, and another assumption that we will make is that your AIs are generated from some Gaussian distribution with general covariance metrics that we don't know. So that will represent the structure. And so now the student comes and he gets just these samples from the teacher. And he kind of had the hunch that he took the inner product between his parameters and the image, so he does the same. So he's also building a function, but now a different function because he doesn't know what is phi. But he also doesn't know what is the exact dimension of the weights of the teacher. So he built his own function, and he will do the minimization with respect to this x. And another example, so this can be represented in terms of this logistic regression example that I've shown before, but another example of that can be a very, very simple neural network in which I can build this function by just thinking about this is my input that I multiply by a set of weights, and I apply some nonlinearity, and then I'm summing over, like, let's say I have L nonlinearity. So if in this picture I have just 3, and I'm just summing over them. So that can be also covered by this type of model. And what is nice about this representation, so So another thing that is important to make is that in all what I'm assuming, so X is a matrix of dimension L and D, and then the same as X star. But in everything, I will assume that D is the effective number of parameters. So D is the extremely large dimension. That's just for convenience to make things easier. And the population loss now, if I'm thinking about, I want to kind of calculate the distance between the function of the teacher and the function of the student. So in the end of the day, I can just write it in terms of a function between the inner product of the weights of the teacher and the inner product of the weight of the student and the noise. So effectively, the distribution of the data is determined by the distribution of the images of the images themselves, let's say the vector of the image, and the noise. Up to here, the model is clear. Okay. And so let's start with the simplest case. Let's start with I'm taking my AI, this is my input, and I don't have any structure. I'm just thinking about just feeding random nodes. So what will SGD will do in that case? So what we found out, so if we go back to, and I'll remind you the iterate of SGD. So this is, for me, because D is very large, then this is very high dimensional. How would I could find some low dimensional representation, which I can study? And this is what we can find. So I know that here has order parameters, which is terminology from physics. But the idea here is that I'm taking a lower dimension representation, which is represented in terms of the norm of my parameters and their overlap with the true parameters. Okay, so if I follow these two objects, then I can show that actually they have some kind, I can track how these objects behave, and I can have an exact ODE that satisfies them. And in particular, what we show is a kind of a law of large number. It tells you that these two objects concentrate, and they can be represented by an ODE that I will show in a second. And you can see that this is with overwhelming probability. As D grows large, you will have that this deterministic limit will be the example. And one important thing to note here is that we are doing some kind of scaling in time. So one iteration of SGD is essentially the iteration in my new process. And the idea is that instead of, as I've shown at the beginning for the fixed dimension, that taking continuum limit was by taking the step size to be very small. Here I'm taking the dimensionality of the parameters to be very large, and that gives me the limit. And what is important is that now I can write a set of equations for this norm and overlap, which is, the first part is essentially the gradient term that is equivalent to the gradient flow. And the second part is related to the noise, and really this is characterized how the noise behaves. And the noise is essentially coming from the fact that at each iteration, I'm not calculating my gradient with respect to all my samples, but I'm just calculating it with respect to one sample at a time. And therefore, the noise that enters to me is essentially the matrix that is created by the gradient of my function. And this matrix has an importance in statistics. It is called the Fisher information. Okay, and actually this type of equation was already presented for a specific model in the statistical physics literatures already in the 90s. So this was presented by this seminal work by Saad and Sola. in which they studied, again, a simple model of teacher and student, in which the teacher was a neural network with set of with fixed number of neurons, and the student, so they essentially generating data from a neural network, and the student was also a neural network, but with different numbers of neurons. And they consider, again, this non-structural data with square laws. So I just want to know that that doesn't cover the example, for example, of logistic regression. The logistic regression doesn't enter into this specific example that they had. But already then, this generated a lot of interest and works after that, that people even try to think, okay, when actually these equations are correct. And 2 years later, they came up with kind of conditions for convergence. Still not a proof, but conditions for convergence. And recently, there was also a lot of interest both in the mathematical literature, but also among physicists to try to study also what happened beyond these cases and extending this for more relevant machine learning examples. But this was done again for the non-structural data case. For the structural data case, again, just with square laws, there was recent work for linear regression, also by my collaborators. But again, this uses a lot the fact that you have the linearity here. And for the nonlinear case, the equation was recently posed for the two-layer example without proof, and they posed as a conjecture by physicists. So, what is so hard with this non-identity covariance case? So the problem with this non-identity covariance case is that I cannot do what I did before. I cannot just write an autonomous set of equations for my norm and my overlap of my iterate. So this is not possible, and the reason for that is that you will have higher powers of k's that will appear, and you cannot close now the equation. So the idea that we kind of take from random matrix theory is to use the resolvent. And using the resolvent, what does that help with? So let's state a few nice properties of resolvents. So one property of a resolvent is that if you multiply the resolvent by the metric itself, then you get back the resolvent. And another property is that if you can actually expand the resolvent and essentially get any power of k. So that is nice, because now I can just write any polynomial k by just doing a contouric integration that encompasses all my eigenvalues, and therefore write any polynomial function in k. So how can I use that in my example? So here what we do is that we actually want now to find new order parameters, new variables that we can track that have low dimensionality. So what we do is essentially to write a norm, but with a matrix of a resolvent. So heated inside by the resolvent, and the same thing with the overlap. And using this idea, we can establish the same law of large numbers that indeed tell you that you have a deterministic equivalence that you can show. And now the nice thing is that now you can actually write an autonomous set of equations. So the equation for f is a little bit more complex now, because it will include all this the complex integration plane and everything, but it will have the same structure. So you will have, again, a term that is related to the gradient and a term that is related to the noise. And I will show how we can simplify that for the specific examples.
So this is for any Z, you get an equation, or
Yeah,
is it for
and Z.
So it's not really lower dimension. It's like a transform, just choosing a different.
Yeah, but
basis.
in practice, what you do for specific examples is that now you can reduce it, for example, to track just a loss function, for example, or if you want to track the norm of your iterates. So these objects will be low dimensional, and you can, using this form high dimension, potentially high dimension formula or equation in function space, you can reduce it to set of examples. So this work for general covariance matrix structure, and going exactly to your so how do I write from this equation the loss function? So the idea is that because my loss function is a function only of the inner product of x and with a and x star with a, and these are just Gaussian vectors that their norm and correlations are essentially related to one another just with one power. Okay, so I can write it using my equation for the resolvent, because now I can just introduce it in terms of linear function in K. So essentially, I can now, solving this equation for the resolvent, I can plug it in and write what would be the loss. But I can actually write any function that I want with any polynomial. And this actually, that's what I will show in the second part of the talk. I can use it actually to provide some learning rate threshold, which will be depend now on the structure of my covariance. Okay, and so if you don't like this high dimensional representation in terms of the Z now, you can actually write it in another form, this result, which is essentially the way we thought about that from the beginning. And the idea is that I have, it's also related to how we are proving the results. So I have my Markov chains, and what I'm doing is I'm looking for a process which will be close to my Markov chain, such that the martingale error will be small. That's kind of the idea. So the process that we find is the following process, which the first part is really what you would have if you didn't have the fact that if you would not, you were not in high dimension, essentially. You were like thinking about the gradient flow. And the second part is really related to the noise that enters because I'm taking each time one iteration at a time, and therefore I have the same noise that also appeared in my ODE. So it's related to this Fisher matrix and my covariance structure. And using this, this process is scaled in time such that each iteration of SGD is the iteration in this process. And the idea is that now I can again write a log-large number on a large class of function, or actually an infinite class of function, such that if I take the SGD and I take this new process and I compare them, then they will be close. And I want to say that this is actually the two processes themselves are not close to one another. This is not necessarily true, but on this class of function that will be true. So if I'm going back to the picture that I've shown at the beginning, between the comparison between the classical picture and the modern picture. So what we think about is that this new process that we denote homogenized SGD represent the limiting equation, but important to note, I put it in quotation mark because this is only on this infinite class of function. Okay, so this was very abstract up to here. So how do we use it to study examples? So let's start with the simplest example that one can think of, which is linear regression. So I'm thinking about my teacher. It was just taking my samples and multiplying it by some unknown metrics and potentially adding some noise. And this is what I'm giving a lot of samples like that to my students. And the students, he knows that that's what the teacher did. So he just built against a linear function. So in this case, you can actually write exactly how the loss looks like in terms of the iterate, but the problem is that you need to calculate these iterates. But if you use, again, our theorem, what we can show is exactly a formula for the loss function, which now you can completely compute. And this idea is, as I said, was related also to the previous work for my collaborator that had for the linear case. And the idea is that, and what is important is because we have this non-identity covariance case, and we expect that actually we can extend the result that we have now, not just for the case in which I'm using one sample at a time, but I can reuse samples. So they did it for the linear case, but now that we also have the result for the nonlinear case, we expect that this is possible, and I will discuss what are the difficulties at the end. So going back also to this logistic regression, I started with the binary logistic regression, but actually you can talk about many classes. Suppose that you have images from, I don't know, cat, dogs, and horses, for example, and you want to classify the data in that case. So you can again build what will be the probability of each example to be in one of the classes. And calculate now something that is called the cross entropy loss, or essentially the Kubler-Kleiber divergence between the two probability distribution between my y's and the probability distribution that I built for each class. And now we can actually build we have an exact formula for the risk, and this is essentially what I've shown at the beginning, that we can provide exact formula of how it will behave in the high dimension. And this is provide an example in which the loss function is not just the square root function. The last example that I want to show is something that is related to the problem that it's not convex. So this is a kind of well-known example in the context of machine learning. It's called phasing people. The idea is that I want to recover my vector x star, but I'm just getting projection of it. So I don't know what is the phase. So I have my x star, and I want, and so I'm building a similar model of a model with projections with another vector x. And I expect, and what I want is that x will be as close as possible to x star. So the issue with this problem, and this is why non-convex problems are hard, essentially, is also because when you start the iteration, so you start with, let's say, I don't know anything about this x star, so I will just start with, let's say, just random. Suppose I'm just finding a Gaussian random vector. So the problem here is that if I take two random vectors in high dimension, x0 and my x star, then I expect that the overlap would be something like 1 over square root of d if they have no correlation between them. So So that's created problems because it means that it will take you a lot of time to build this non-zero overlap. And actually that can be shown that it will take something like d log d iteration to build that, which in principle is out of our theorem, but actually we can show that we can recover that as well. And another hack that you can do around it is to say, okay, let's say I do know something about the direction of x star, so I'm starting from some overlap that will be non-zero overlap. So we will have order one value, and then the iteration, the number of iteration will be order over the. But actually, you can also see that if you just look at our equation, in particular, what we plot here is a kind of a vector flow of the dynamics. So this is the cross, essentially the overlap, x transpose x star. And this is the ratio between the flow norm and the norm that is being estimated, the x. And so you can see that this is actually depend a lot by the learning rate. So if you start with a very low learning rate that will be more proportional to what gradient flow will do, so it will take you a long time until you will build up this overlap. And once you build the overlap, you also build the norm. And if you start with a higher learning rate, then this will happen a little bit faster. But you can also see that from looking at the loss itself. So if you look at the loss itself, you can see that you're getting stuck at the saddle point, that you will be stuck there for a while if you're starting with a very low small learning rate. And the same thing happens here. If you look at the overlap as a function of number of iteration, it takes much more time to build the overlap. Okay, so this is just a few examples of that our framework can cover. There are many more. But in terms of, I want to discuss now about how can we use this type of result to also provide stability and convergence of stochastic dynamism. So to kind of ensure that the algorithm indeed converges and not diverge and does something that we don't want. So this is a question essentially in optimization. Kind of asking what learning rate will actually ensure that we actually decreasing it. So what is the difficulty with stochastic algorithm? The difficulty with stochastic algorithm that it's, if you want to do that, then you have a stochastic dynamics that is really hard to track and provide some kind of threshold that will be fixed for any dynamics. But luckily for our what we have is that we can actually use our deterministic limits. So how are we gonna do that? So the idea is that you look at some you want to find some function that is decreasing. So this is something that usually is called the Diacono function. So the idea is that the function that we take, suppose now that x and x star are of the same dimension. Not only that, I'm just looking at their difference. And I can find an equivalent deterministic limit using our theorem. So essentially, it's suffice to look at this deterministic limit now and just I'm translating the question. So instead of looking at what will be the learning rate for the descent, I'm looking what will be the learning rate in which my distance, my distance, deterministic distance will decrease. And I have actually a precise formula for that. So now I can really look at this formula and say, okay, what will be when this will descend. So the first term is again some terms that involve the gradient itself, and the second one is a term that involves again the noise part. But what is important is that now I can just ask what I have a dynamical threshold, which essentially will depend on the ratio between these two terms. Which, when you have some kind of nice properties of your problem, if you have convexity or smoothness, then this dynamical threshold can be actually constant. And this can be related, for example, for the Lifshitz constant of the gradient, for example. But what is kind of nice here that the structure of the structure of my covariance matrix enters into the game. So this, by the fact that I'm now so now it doesn't depend actually on the largest eigenvalue, which is something that usually will happen in this type of result, but actually it will depend on the average eigenvalue, and that allows us to kind of provide convergence for a larger set of learning rates, in which you would think that the algorithm will not converge. And we can also provide convergence rate, but this usually requires additional assumptions such as convexity. But what we can show when you do have convexity, then that the rate of convergence will be related to the average condition number of my covariance matrix, which is different than what you will usually have, which will be rates that will be connected to the condition numbers. And this actually, for example, covered the problem of logistic regression, in which you're not strongly convex, but you are locally convex, but this is still, we can still cover it using this type of result. And just to show how this indeed depend on the covariance matrix structure. So what we did here is we look at this distance to optimality with respect to the last iterate as a function of the learning rate for different covariance matrix structure, which we generate them in this form. So we have the covariance matrix that has a power law distribution. And we scaled all of them to have the same average eigenvalue. So what you can see that indeed we get that they all have the same threshold in which this distance to optimality is descending, and from that threshold you're kind of not converging. But you can see that actually the convergence rate itself is different, and that indeed depends on the maximal and minimal eigenvalues as we would expect. Okay, so to conclude, so I provided a general framework of how to do stochastic optimization, how to analyze stochastic optimization in high dimension. And we have concise and exact formulas in which we can really track the dynamics in high dimension, in particular for SGD. And I provided this optimality condition that can also be generalized further, and you can see how the structure of the covariance matrix enters into the game, which we can also extend also to the cases in which you have some time-dependent learning rates, or in cases in which on top of, suppose that you do know something about the structure of your parameters, so then you add some other term to the loss. So in that case, this is something that is called regularization. So we can also do that using framework. And we also are able to show some kind of, there is a lot of theories with respect to what SGD does in practice. So one of the kind of terminology that people put to it is something that is called implicit bias, because it seems in the context of machine learning that SGD somehow find good solution without putting a lot of regularization on, without putting a lot of effort into it. So one of the reasons for that is, and we showed in particular examples, is that it kind of have, and this is something that people conjecture, is that the solution that they find has some lower norm. And you can actually see that in particular examples that we provide, that indeed, because of the noise that we can now exactly know what is the structure of that noise, we can show that indeed SGD will converge the solution that has a lower. And now I promise that I will talk about how working with generalized covariance matrix can allow you to study other algorithm, for example, an algorithm when you can reuse the data. And this is also related to some other questions that you might be bothered, for example, because our data was, we assumed that it was Gaussian, but actually a lot of our statements and how we prove them use a lot of concentration phenomena that doesn't have to be only with Gaussian. So this, we do believe that that can be generalized, and we expect that that will be, we can get a more universal result. But the main, so this I think will not be the hard part. So the hard part in terms of generalizing to a case in which you can reuse samples is the fact that we kind of require that we will know X star, and which for the linear case is kind of can be kind of either our way around it because of the linearity. Instead of using X star, you can use the Y itself. Why does that bother us? Because what we would like in the end is that you take our equation and you just plug your data instead of so in that case we would have liked that we will not have this dependency on X star, and we currently have some ideas of how to do that as well. Another question that I'm particularly interested by is about information theoretic threshold. So SGD is just one algorithm to solve this problem of the teacher student, but you can try to find other algorithms to do this. And in particular, something that people do in the context of information theory is to try to find what will be the error for any algorithm that you can find. So we do have already such results that shows what we have a lower bound on the error. So it would be interesting to compare and to show how SGD is doing with respect to this lower bound. And there is also some other result in the literature in that context. Another idea that I'm also interested by is how to extend this to when you have not just one layer in the context of neural networks, but many layers. So this is something that is much more harder to do. So we know how to do that when you don't have dynamics. So if you just look at your last iterate only, that we kind of know how to do. But analyzing the dynamics is hard. This is something that is still open. And there is also a lot of questions that are related to phase conditions. One of these type of phase conditions was what I've shown with respect to phase retrieval, that you have this area of saddle point in which it's harder for you to learn, and then you want to start learning. And so this can be shown not just in the context of phase retrieval, but in a large class of models. So it will be also interesting to apply the theory for this type of models. And something that we actually analyze already now is something that is called adaptive step size. So usually when people run these algorithms, choosing the step size is an art. You need now to try to find what will be the right step size to work with, in which you will get good convergence. So one way around it is to take the step size to be random variables as well. So now you think about, and the way you build it is in a way that it has some knowledge about your previous gradients. So somehow the algorithm adapts in such a way that in the end it finds the good step size. And so the problem in analyzing such a system is that now I'm moving from a system that is Markovian to a system that is non-Markovian. But we still have a way actually to do that, and we can provide and high dimensional in that case. So this is still a work in progress. Okay, thank you.
Thank you very much. Do you have questions?
So at least at the low dimensions, one of the problems, there are many problems to gradient descent, like getting stuck in a local minimum or that you have to take many steps. And people say that stochastic gradient descent actually improve of that because you can, for example, if you go actually in a wrong direction, maybe at the end of the day it will be better. So does this kind of, if you show that stochastic gradient descent converges to the gradient descent, does that mean that actually SGD stochastic can be better than what you get? Or
so you mean if stochastic gradient descent will be better than gradient descent?
yes, then
so one example was this this idea of implicit bias, that indeed you can show that in some cases, using this noise, it can be beneficial, and it helps you to find a good solution that you want. I do think that, and it's also, there is a lot of controversy about that. So it does, what actually the noise is actually doing. So in some problem, it could be another way, but what we can show here that because we have this precise equation and the structure of the noise, we can actually know exactly when will it help you and how it can help you.
So all these effects should be a part of the noise term that
of the noise term reduction that we can really track.
More questions?
You mentioned at the beginning that, let's say, ChatGPT, there's 175 billion, 100 trillion parameters. So if Sam Altman or whoever else is currently the CEO was sitting here, would you tell them they should use this and this would speed up?
Oh no, I'm not. Well, the first thing that I would say is that I'm not building new algorithms. My purpose of what I do is to try to understand what are these algorithms doing. So there is a zoo of algorithms that are already being proposed every day. so that's kind of not my. So my goal is to try to build some theory based on simplistic example that we can understand and see whether we can kind of provide some guideline to what actually practitioners are doing in practice. So and along the way, discover interesting other ones.
So you prove more than the physicists prove.
Yes, that's I'm actually working on that to more regimes.
More questions?
so the threshold for stability, if I understand that depends on the true model.
Yes, it depends on. I mean, in some cases, when you have this convexity or some kind of smoothness, then you can provide some threshold that would be more general, but it does depend on the model.
Can the speaker of them?